Section 5.4, medians and altitudes in triangles. We're going to use the medians of the triangle and the centroid to find missing values, and we're also going to talk about altitudes and the differences between all of these segments that we've been drawing in triangles. So, the median of a triangle is the segment from a vertex to the midpoint of the opposite side. So, here is the midpoint of the opposite side. We can see that by the marking. And this is the vertex right here. So this is a median right there. But there are other medians in a triangle as well, because if I find the midpoint over here, then I could have another median, just like we had other angle bisectors and other perpendicular bisectors as well. So this is another median, as well as this one right here. Now, this is different from a perpendicular bisector. Remember, a perpendicular bisector bisected the segment, so it would still meet here, but it would be perpendicular, and it does not come from a vertex. So this is a perpendicular bisector. So we want to make sure we understand the differences between these segments. It turns out that the three medians of a triangle also meet at a point of concurrency called the centroid. And this point right here, point P, is the centroid of this triangle. And its significance is that the centroid, that point, is 2/3 of the whole distance. So in other words, it's 2/3 of the distance from each vertex to the midpoint on the opposite side. So it means that AP is 2/3 of the whole length AY. Well, if AP is 2/3, then it makes sense that PY would be 1/3. And again, that's what we have at that point of concurrency. Now, again, this also would be true for other medians in here. So if you take the point B, the vertex B, and you go to P, that distance will also be 2/3 of the whole length. So in other words, we could also say that BP is 2/3 of the whole length BZ, etc. Okay, so let's try some examples where we use now the centroid, which is the point of concurrency from the medians. So this example says G is the centroid. So you either have to be told that, or you're going to have the appropriate markings to know that that is a median, which you don't right now. You're also given that AD is 8, that's already marked right here, and you're given that AG is 10, that's already marked right here. And then you're given CD, you're given this whole segment right here, CD, the whole segment is 18. So let's find BD. Okay, so the first thing we're going to find, and we're going to find this segment BD. Well, remember, this is a median, so it goes to the midpoint, so those two are the same. So BD would also be 8 units. And AB, we just add them together to get 16 units. Okay, let's work on EG. Now we want to find EG right here. Well, we know that from A to G is 2/3 of the whole length. So that means that AG, that we already know, is equal to 2/3 of the whole length AE. Well, AG is 10, so that's 2/3 of the whole thing. Let's call it X for right now. So now all I do is solve by dividing by 2/3 on each side, which gives me a value for AE of 15. Oh, and they want me to find that anyway. So the whole value of the whole segment is 15, and if the 2/3 is already 10, that makes this 5. And again, if you think about that, if 2/3 is 10, that's 2 pieces out of 3, and so each piece would be 5, and 5 makes 10, plus another 5 makes 15. So there's multiple ways of kind of looking at this. 2/3 of the whole thing, or 2/3 and 1/3 is another way to look at it. And now let's work on CG. They want us to find CG next. Well, we know that the whole thing is 18, so we know that CG is equal to 2/3 of the whole thing, CD. So CG is what we're trying to find, and it's 2/3 of 18. Again, we multiply this out, and CG is 12. So 12 units, and if the whole thing is 18, then DG has to be 6, even just by subtracting. Okay, so now we kind of go through the same process, but now we're going to have to set up some expressions and equations to solve. So it tells us that G is the centroid. So remember, this is a median right here then, which cuts this in half. Okay, so keep that in mind. It might look like an angle bisector, okay, but it's not necessarily. And so now let's see. They want us to find the value of x if CG is 3x plus 7 and CE, the whole thing, is 6x. So then what we know is we know that CG is 2/3 of CE, or 3x plus 7 is 2/3 of 6x. So again, multiply 2/3 and 6 together, and that gives you 12/3 x, or 4x is equal to 3x plus 7. Now we get the x's on one side and the numbers on the other, and that's a pretty simple x equals 7. All right, let's look at the next one. Now we are given that FG right here is x plus 8. And we are given that AF, the whole thing, is 9x minus 6. So remember, this is 2/3. From the vertex to that centroid is 2/3. So that makes GF, or FG, 1/3. So that means that x plus 8 is equal to 1/3 of 9x minus 6. Or I guess if I write it out, we know that FG is 1/3 of the whole median AF. And now when we use the distributive property, we're going to get 9 over 3, or 3x minus 6, equals x plus 8. Getting the x's on one side, that gives me 2x equals 14, and it looks like we have an x of 7 as well. And the last one I'd like you to try. See if you can set it up. So we have BG is 5x minus 1, and DG is 4x minus 5. So what we also know is we could set like the 2/3 plus the 1/3 equal to the whole thing. But we also know that BG is 2/3 of BD, the whole thing. And we're given BG So 5x minus 1 is equal to 2/3 of dg. That's 1/3, so that's not going to help us out here. But we do know that, as I said before, we do know that bg plus dg equals bd. And so if we add these expressions together, 5x minus 1 plus 4x minus 5, now we will have bd in that other equation we had. So 9x minus 6 is what bd is. And so bg is 2/3 of bd. And so now we have the expressions we need. We have bg, which is 5x minus 1, is equal to 2/3 of bd, which is 9x minus 6. And you can go ahead and solve that, and I'll put that up in the notes so you can check your work. So now let's look at a little more challenging problem, multi-step. It says graph triangle JKL. I did that already for us so that we don't have to wait for me. Now it says find the coordinates of M, the midpoint of JK. So somewhere over here I have a midpoint M. So I use the midpoint formula to do that. I take J right here and K, and I take the average of the x's. So I take 6 plus negative 2 over 2. And I take the average of the y's, 7 plus 1 divided by 2. So my midpoint is 2, 4. So 2, 4. So now I'm going to use the median LM. So I'm going to draw in this median LM. Right there, that's a median. It went to the midpoint, right? From the vertex to the midpoint. And I'm going to use that to find the coordinates of centroid P. Well, because this is a vertical line right here, I can just use the ruler postulate or counting. I could use the distance formula, but I really don't need to because I can see that it's 9 units long. So LM is 9 units. So that means that the centroid P is going to be 2/3 of 9. It's that length of P is going to be 2/3 of 9. Or I guess I could say LP, from L to P is 2/3 of 9, which is going to equal 6. So that means it's going to be 6 units, 1, 2, 3, 4, 5, 6. So that is where P is. And now we can find the ordered pair for P, which would be 2, 1. Okay, so now I'd like you to try to find the coordinates of N, which is the midpoint of JL. So N is the midpoint of JL. So now you're going to use J and L to find the coordinates of N. And then you're going to verify that KP is equal to 2/3 of KN. So your K will be somewhere over here. And then you're going to use the distance formula to find KP. And you're going to use the distance formula to find KN and compare them. So go ahead and try that example and then check back to the notes to check your work. The last thing we're going to talk about is altitudes. So an altitude is really the height of the triangle. It's the perpendicular segment from a vertex to the opposite side, or a line that contains the opposite side. So again, this one, the altitude comes from the vertex, like the angle bisector and like the median. The perpendicular bisector does not. But the key is it goes to the opposite side and it's perpendicular. That's important. It has to be perpendicular. Now, if you have an obtuse triangle, your altitude is going to be outside. If you have an obtuse angle, at least at that point. But again, you have other altitudes. So if we draw in a different altitude in this first triangle, I'd go from the vertex, and it would be perpendicular to the opposite side. And the altitudes do meet at a point of concurrency called the orthocenter. So all of them would meet at a point of concurrency. So if I draw in this last one on this particular triangle, that point of concurrency right there is called the orthocenter. Now, there is no special significance of the orthocenter besides that we call it the orthocenter. But there's some pretty cool things that happen when you have an isosceles triangle or an equilateral triangle. And it turns out in an isosceles triangle, the perpendicular bisector, so if I draw in the perpendicular bisector, so it's bisecting this side and it's perpendicular. But notice that that segment is also bisecting the angle right here. It's also the angle bisector. And that segment is also considered a median because it comes from the vertex and goes to the midpoint, so it's also a median. And it's also the height or altitude. So that segment in an isosceles triangle, okay, from the base angle, or from the vertex angle to the base, that is the one that will be all the same segment. And to extend that a little further, if you had an equilateral triangle, then you actually have kind of all of the angles are base angles. And so in an equilateral triangle, all the perpendicular bisectors, angle bisectors, medians, and altitudes are all the same segment from every vertex. In an isosceles triangle, it's just the same segment from that vertex angle to the base. So that means that all of the points of concurrency, the circumcenter, incenter, centroid, and orthocenter, are all the same as well. So just kind of some cool significances in some special triangles.